Introduction to integrated testing. Definition of integrated testing. Integrated testing is the testing process in software testing to verify that when two or more modules or interact and produced result satisfies with its original functional requirement or not. Integrated testing will start after completion of unit testing. Software testing engineer is performing integrated testing. Why integrated testing is required? Integrated testing finds the bugs that occur when two or more modules integrated. Main purpose of integrated testing is to identify the functional requirements and performance level bugs. When modules are not integrated, they perform as per requirement, but when they are integrated, functional requirement and performance related issues will occur due to the integrated. Testing methods. The different testing methods such as board level testing, in-circuit testing, and functional testing is shown. Board level testing. In-circuit testing. Functional testing. Board level testing. Board level testing. In this testing, all the individual chips are tested by checking the response of the system rather than the chip alone. All semiconductor devices, once tested and verified, will have to be placed on a printed circuit board in order to form a part of the digital circuit or system. Interconnections are not explicitly tested, but an interconnection fault manifests itself as failure of some chip during testing, so it is indirectly detected. The whole manufacturing and design process has interfaces with a manufacturing resource planning, that is MRP system, supported by a corporate-wide MRP database. MRP database is used as a method for effective planning of all resources of a manufacturing company. The system is designed to centralize, integrate, and process information for effective decision-making in scheduling, design engineering, inventory management, and cost control in manufacturing. CAE or CAD design process. In the CAD-centric process, the design is done in CAD system and then in an iterative design process, where design changes and analysis is repeatedly performed, which is used to improve or refine the design. CAM uses auto-insertion machines to place through-hole devices on the board, and it uses pick-and-place machines to mount surface-mounted devices, that is SMDs. When all the SMDs have been positioned, the board is soldered using wave soldering. This involves heating the solder paste until it flows into a uniform solder layer which permanently affixes the SMD pads or leads to the board. Bare board testing. Bare board testing frequently employs a known good board and then compares all other boards fabricated with it to detect any manufacturing defects. In-circuit testing. The in-circuit testing approach involves measuring the performance of individual components by electrically isolating them from the rest of the circuitry. In-circuit tester will start running and the monitor will display the progress of the test. Finally, it will proceed the test is pass or fail. If the process is failed, the in-circuit tester will detect the fault in the board and rectify it. Functional testing. Functional testing checks the behavior of the assembled board against its functional specification with the power applied and with stimulated or special test signals connected to the input-output lines. Although CAM technology facilitates the manufacturing process, it does bring additional problems for testing board level assembly of a digital system. Physical defects such as a bent pin or incorrect parts can be introduced by the associated automation equipment and processes. To deal with these problems, additional testing steps are introduced. The board level testing falls into three categories. They are bare board testing, functional testing, in-circuit testing. Calibration of digital multimeter. In this video, we are going to see about the calibration of digital multimeter, that is DMM. Depending upon the received calibration state of the DMM and the customer's requirements, three different sequences of operations can be performed. They are pre-adjustment calibration, calibration, adjustment. Pre-adjustment calibration. Pre-adjustment calibration provides information on the behavior of the instrument in the period that has elapsed since the previous calibration. Pre-adjustment calibration consists of adjustment, post-adjustment, adjustment. Adjustment brings the readings of the instrument within the limits of manufacturer's specifications. post-adjustment? The post-adjustment calibration documents the state of the instrument after the adjustment has been performed. If the instrument turns out to have maintained its accuracy in a highly satisfactory manner, it is possible not to perform adjustment and to follow next sequence, that is calibration. Calibration. The limits which must not be exceeded by the calibration results in order for this to be possible must be selected in such a way that the instrument remains presumably within specification during the following period of use. For example, for non-high accuracy instruments with manual type adjustment, which usually have low drift with respect to specification, the limits to the deviation between the applied quantity and the reading can be set at 70% of the annual specification declared by the manufacturer at all the measurement points. The limits to the deviation between the applied quantity and the reading can be set at 50% if the point corresponds to a value for which the instrument was adjusted. For other more accurate instruments, the limit can be set at 50% of the specification for all measurement points. If the calibration state of the instrument when it arrives at accredited calibration laboratories, that is ACL, is not relevant to the customer, it is possible to omit the preliminary calibration and to follow the next sequence, that is adjustment. Adjustment may be the case if the instrument has never been submitted to periodical calibration or if operations have been carried out, for example, repairs that have significantly altered its metrological characteristics. Adjustment must be performed according to the method prescribed by the manufacturer. All the operations listed in the instruction manual of the instrument must be carried out except for those of an exceptional nature. Usually, calibration procedures must be performed configuring the instrument in such a way as to be able to obtain the best measurement accuracy. For high accuracy DMMS, to reduce the calibration time, a less demanding configuration can be used if the increase in uncertainty is negligible with respect to specification. Example 1. To measure the temperature and display it on an LCD display. Given data, temperature sensor, that is LM305, is equal to 10 mV for 1 degree Celsius is equal to 10 mV per degree. 16-bit ADC microcontroller is equal to 212 no unit for every 1 volt is equal to 212 per volt. Input regulated power supply is equal to 1 volt. If ADC microcontroller is equal to 1060, temperature is equal to what? Calculation. Microcontroller noise per volt is equal to 212. Observed value at the ADC is equal to 1060. So, the number of volts at ADC input is 1060 by 212 MC noise constant is equal to 5 volts. Now, we know that a sensor can generate 10 mV per degree. Now it has generated 5 volts as per the calculation. Example 2. Let us consider One more example of a battery level indicator having a calibration potentiometer. 100% battery power is equal to 12.6 volt for 12 volt battery. Discharged battery power is equal to 11.7 to 11.9 volt. Drained battery power is equal to below 10 volt. Battery voltage is equal to 0.7 volt for 0% to 100%. Consider that the battery level indicator has 10 LED, so 1 LED is equal to 10% of power. Solution: set 11.9 volt in RPS. Calculation: total voltage difference is equal to 0.7 volt for 0 to 100%. 10 LEDs is equal to 10 levels is equal to 0.7 by 10 is equal to 0.07 voltage. So, 0.07 volt is equal to 10% battery. So, 11.9 for 10% plus 0.07 volt is equal to 11.97 volt for 10%. For this value, first LED should be lighted up by tuning the calibration potentiometer and adjust the RPS in steps, then light up corresponding levels of LED and complete the calibration. Now, the calibrated device can be deployed to measure any 12 volt battery. Example for digital multimeter calibration. In this video, we are going to see about example for digital multimeter calibration. Calibration of digital multimeter consists of purpose, scope, procedure, reference material, specifications, equipment required, setup, battery replacement, detailed procedure. Purpose. The purpose of this procedure is to provide instruction for the calibration of digital multimeters DMM. Scope. All multimeters, that is, multi-range instruments used to measure voltage, current and resistance ought to be verified in calibration no less than once per year. Procedure. For the procedure, first the preliminary instructions and the notes are given. Read this entire procedure before beginning the calibration. Calibration shall be performed in an environment that conforms to manufacturer specifications. The digital multimeter will hereafter be referred to as Instrument Under Test, that is IUT. Verify that the IUT is clean and visually examine the IUT for any condition that could cause errors in the calibration. If any of the requirements cannot be met, refer to the applicable manufacturer manual. If a malfunction occurs or a defect is observed while calibration is in progress, the calibration shall be discontinued and necessary corrective actions taken. If corrective action affects a measurement function that is previously calibrated, the function shall be recalibrated before the remainder of the procedure implemented. Reference material. For the reference purpose, we are using applicable manufacturer's manual or brochures. specifications. The specifications of the IUT are determined by the applicable manufacturer's documentation. If the manufacturer's documentation is not available, then the specifications identified in this procedure are used. Equipment required. The standards listed below should be selected on the basis of their higher accuracy level when compared to the unit under test. Equivalent standards must be equal to or better than the minimum use specification. Minimum use specifications for standards listed are 1/4 the accuracy required by the IUT. The instrument used are Rotec model 2500 calibrator or equivalent, diode text fixture, test leads, continuity text fixture, capacitance test fixture, thermometer, hydrometer. Setup. Turn all power on, that is calibrator and the unit to be calibrated. Allow the instrument to stabilize for approximately 5 minutes. Conduct the test in an ambient temperature of 25 plus or minus 5 degrees centigrade and a relative humidity of less than 80%. Battery replacement. Replace the battery in the IUT and make sure the battery contacts are not dirty. Detailed procedure. Display and switch test. Turn the IUT on and verify that all LCD segments are working and not dim. Verify that the selector switch is or working properly. Make sure the low battery indicator is not showing. Resistance check. Connect the calibrator between the volt per ohm and common input terminals of the IUT. Use the following chart to verify the resistant values. Set the multimeter in 200 ohm. Short the test leads of the multimeter and check the output is in between 0.00 to 0.05. Similarly, we are varying the multimeter range and checking the resistance value for various resistors. Continuity test. A continuity tester is an electrical test equipment used to determine if an electrical path can be established between 2 points and connect the test leads to the volt per ohm and common terminals of the IUT. Switch on the multimeter and select the continuity check function on the multimeter. Momentarily, short the test leads together and observe the tone sounds in the multimeter. Connect the test leads to a probe to check the cables are internally broken or not. Connect the test leads to the continuity test fixture between the 50 ohm setup. The test tone should indicate continuity between the test points. Connect the test leads to the continuity test fixture between the 100 ohm test points. No tone should be heard indicating non-terminating connection. DC voltage test. Connect the ground, common, low side of the common on the IUT. Connect the calibrator output to the voltage per ohm and common input terminals of the IUT. Switch on the multimeter and set the range to voltage value to measure voltage for some of the batteries. Set the calibrator to 2 volt and with the help of leads, measure the voltage of 1.5 volt battery. Move the function switch to 20 volt range to measure the voltage of 9 volt battery. Connect the leads to 9 volt battery and the readings measured as minus 8.98 volt so that the battery is slightly depleted. Then reverse the leads and readings measured as positive voltage, that is 8.98 volt. Thus, the process is repeated for several batteries and we can verify that the display falls within the limit. AC voltage test. Select the IUT voltage range and set the calibrator output to the corresponding IUT input voltage. Verify that the display reading is within the limits. DC current test. Connect the output of the calibrator to the current terminal and common input terminal on the IUT. For testing the current of the given circuit, that is 190 milliamps, set the current range of the multimeter as 200 milliamps and check that the output is in between 189.7 to 192.3. Similarly, change the range of the multimeter as 10 amps and for the circuit given, that is 1 amp, the output is in between 0.98 to 1.02. AC current test. Connect the output of the calibrator to the current terminal and common input terminal on the IUT. Select the IUT current range and set the calibrator output to provide the corresponding IUT input current. For 20 milliamps range, the input given is 19 milliamps and the output is in between 18.27 to 19.28. For 200 milliamp range, the input given is 190 milliamp and the output is in between 182.7 to 192.8. Logic test. Connect the calibrator between the volt per ohm and common input terminals of the IUT. Short the leads together and verify that the meter indicates a low logic state. Touch the black probe to the drain pin. Touch the gate pin with the red probe to discharge internal capacitance in the MOSFET. Move the red probe to source pin and use your finger to touch the gate and drain pin together. We can notice that the multimeter shows the values from low logic state to high logic state. Frequency test. Connect an oscilloscope to a function generator to measure AC sine waves. Connect the IUT leads to the volt per ohm and common terminals on the IUT and to the ground and output of the function generator. Set the input of function generator as 60 Hz and verify the output is in between 59.4 to 60.6 Hz. Similarly, for 1 kHz, the output is between 0.990 to 1.010 kHz, and for 1 MHz, the output is in between 0.990 to 1.010 MHz. Capacitance test. Set the IUT to measure capacitance. Insert the test leads into the voltage per ohm and common test terminals. For 10 microfarad, 1 microfarad and 100 microfarad capacitor, the output is between 9.85 to 10.15, 0.990 to 1.01 and 0.990 to 1.010 respectively. Diode test. Set the IUT to the diode check function and connect the test leads to the voltage per ohm and common terminals. While shorting the leads, the output is in between 0.000 to 0.001 and there will be a tone. For the forward function of silicon diode, the output is 0.800 to 0.600 and with a tone. For the reverse function, the output will be 1 and no beep sound. Similarly, for germanium diode, for forward bias, the output is between 0.300 to 0.500 with beep sound, and for reverse bias, the output is 1 without beep sound. In-circuit testing. In this video, we are going to see about in-circuit testing. Introduction. In-circuit testing, the aim of which is to find gross circuit faults before commencing any fully detailed functional testing, may or may not be done. The possible manufacturing defects are: tombstone, solder shorts, poor soldering, missing components, lifted pin, testing process. In circuit testing, electrical connections to the individual components are made via a bed of nails fixture, the processor of the in-circuit tester being programmed to supply and monitor all the required test signals. Here is the typical in-circuit tester with a fixture installed on the tester. The graphical representation of the tester and the fixture is shown. Fixture cover, probes, fixture wires, fixture interface pins, module interface pins, tester pin card, test head. Open up the fixture cover to place the board under test. In order to test the board, the in-circuit tester need to drive signals to and receive signals from the nodes on the board under test. The module interface pin on the tester pin cards will connect to the fixture interface pin. The fixture interface pin a wire to the probes which intend or connect the board under test. This interface provides the path for signal flow between the tester and the board under test. The in-circuit tester will start running and the monitor will display the progress of the test. At the end of the test, pass or fail result is displayed. The testing of the circuit may fail due to tombstoning, solder shorts, missing pins, lifted pin, poor soldering. Tombstone, solder shorts, missing components, lifted pin, poor soldering, the in-circuit test will detect all the faults in the circuit board, and finally the monitor displays the result. Testing process of a component. For a discrete component, a measurement technique is shown. In the typical in-circuit test setup, probes and wires connect the device under test to the measurement circuit on the tester. Here, Z1 and Z2 are the impedance path for either side of the component Zx being measured. By connecting both of these paths to ground, virtually all the current flowing into the in-circuit measuring operational amplifier comes from the test source, that is V source, via the component Zx. Current flowing through Z2 is negligible because of the virtual ground condition. Hence, V out is equal to minus Vs by Zx into RFB. Zx is equal to minus Vs RFB by V out. Different ICs used in testing. What is integrated circuits, that is ICs? Integrated circuit, that is IC, is an assembly of electronic components fabricated as a single unit in which miniaturized active devices, for example, transistors and diodes, and passive devices, for example, capacitors and resistors, and their interconnections are built up on a thin substrate of semiconductor material, typically silicon. Different ICs are small scale integration SSI, medium scale integration MSI, large scale integration LSI, very large scale integration VLSI. Small scale integration SSI describes fixed function ICs that have up to 12 equivalent gate circuits on a single chip, and they include basic gates and flip-flops. Medium scale integration MSI describes integrated circuits that have from 12 to 99 equivalent gates on a chip. They include logic functions such as encoders, decoders, counters, registers, multiplexers, arithmetic circuits, small memories, and others. Transistor logic, that is TTL circuits, which could withstand test pulses of about 10 microseconds duration to drive gate inputs to opposite logic levels. Large-scale integration (LSI) is a classification of ICs with complexities of 100 to 9999 equivalent gates per chip, including memories. In general, LSI chips use MOS transistors as it requires less number of steps for integration. However, TTL becomes impractical for PCBs with a high population of digital ICs, particularly LSI and VLSI packages, and with present-day small geometry, low power gates, and macros. Very large-scale integration (VLSI) describes integrated circuits with complexities of 10,000 to 99,999 equivalent gates per chip. Advantages of in-circuit testing: very fast total system, very high fault coverage also for highly compact PCBs, reduction of nail bed adapter costs, simple test program generation because each test technology is applied according to its core competence. Disadvantages of in-circuit testing: each product needs its own test picture. PCB densities sometimes make probing difficult. Test contact failures can arise when test pins do not make proper contact with the appropriate test pads. Test pins need to be regularly cleaned and replaced. Introduction to calibration. In this video, we are going to see about Introduction to calibration. Calibration is a process of configuring an instrument to provide a result for a sample within an acceptable range. Calibration is a process of deriving a mathematical relation between the applied input and the output to be displayed, or creation of database of the output to be displayed when a certain input is applied. In other words, it is a process of teaching the devices or instruments to measure any quantity, and can also be defined as a comparison of unknown quantity with a standard scenario or quantity, and to mark the level of the unknown quantity. Calibration is essential for ensuring that the equipment being used is measuring correctly and with maximum accuracy. Calibration is the first critical procedure necessary to ensure proper instrument setup prior to starting measurements. Calibration sequence. Calibration sequence depends on three categories. They are gain, offset, TDR amplitude. Gain. The purpose of the gain is to adjust loop gain for damping pulse response. The actions of gain are listed below. Auto calibration. Connect cable to output. Proceed. Store constant. Recall user constant. Offset. The purpose is to set offset of TDR pulse. The actions of offset is listed below. Auto calibration. Terminate cable with 50 ohms load. Proceed. Store constant. Recall user constant. TDR amplitude. The purpose is to set TDR amplitude. The actions of TDR amplitude is listed below. Auto calibration. Terminate cable with 50 ohms load. Proceed. Store constant. Recall user constant. Test equipment calibration. In this video, we are going to see about test equipment calibration. The essential facts about test equipment calibration is to enable the best to be gained from the test equipment. In order that any item of electronic test equipment performs to its specification, it is necessary to ensure that it receives its periodic calibration. Like any other item, electronic test equipment tolerances change slightly with time and temperature. It is possible to minimize the levels of drift, but they cannot be totally eliminated. Only when an item of test equipment is within its calibration period, it will be guaranteed to produce results that are within its stated specification. Once the calibration period has been exceeded, then it is not possible to guarantee the results. When using an item of test equipment, there are some circumstances when the calibration of the test equipment is required. Under other circumstances, it is not. It may be that a measurement is only required to provide a rough order of magnitude reading, and for this, a fully calibrated test instrument may not be needed. However, for development test, production test, and other areas such as qualification test, it is crucial that the results from the test equipment can be guaranteed. Under these circumstances, it is necessary to ensure that the test equipment is within its calibration period. In view of the fact that most test instruments and other pieces of test equipment are used for both ad hoc measurements as well as those for more formal test applications. It means that all test equipment available for use should be calibrated. While calibration adds an additional expense to be covered by the company, the consequences of not having all equipment calibrated is far more costly.